Okay, I assume these slides are all right. Assume everyone can see the slides.
Yes.
Okay, so I am going to be talking about indirect associations and learning semantic and syntactic relationships. This is research I did at Penn State. And uh, there's a paper that's currently under review. You can find it at the DOI link on the first slide here. All right, let's get into it. Um, so first of all, I'm a cognitive scientist. So my background is in psychology and computer science and linguistics and human memory. Um, so I'm going to briefly mention a couple of my previous papers. I've done a number of papers deal with vector symbolic architectures. My first was looking at taking Tony Plate's holographic reduced representations and using them instead of taking random vectors as input. I was taking like images as input, like photographs such as this church here, and essentially looking at what do you need to do to work with those. And that all you have to do is you have to permute them randomly, and then they're perfectly serviceable. Um, this paper also does a little bit of comparison of different vector symbolic architectures. So people are looking for more comparisons of the different vector symbolic architectures. This paper exists. After that, I ended up doing some work with vector symbolic architectures and using vector symbolic architectures to model human learning of a decision-making task. And some of my more recent work has been looking at vector symbolic architectures as a model of human memory, and particularly showing how the geometries of these high-dimensional vector spaces do a very good job of predicting human forgetting and human response times in experimental tasks that test human memory. So today I'm going to be talking about a language application of vector symbolic architectures. And so there's a number of reasons to study language. One is to improve our theories and models of human and artificial intelligence. Language is one of the most difficult things that humans do. So if we can replicate that capacity in computers, we have presumably learned something, hopefully a lot, about how human intelligence works. Better understanding how humans learn languages can improve our ability to teach languages in the classroom, diagnose language deficits, and of course, it has AI applications such as dialogue systems such as Siri and Cortana and Google's Google Assistant, machine translation, web search, document understanding. So today I'm going to be focusing on the semantics versus syntax distinction. So semantics is what a word means or what a phrase or sentence or any amount of language means. Syntax is about how you construct language according to the rules of the particular language. So, for example, this is illustrated quite well by two quotes by two wise individuals. One is Yoda, and Yoda is famous for, Yoda from Star Wars is famous from the way Yoda talks. So like, named must be your fear, before banish it you can. An example of something that Yoda says. And the other quote I have here is from Noam Chomsky, and it's colorless green ideas sleep furiously. And so these two sentences illustrate the distinction between semantics and syntax quite well. So Yoda's sentence, named must be your fear, before banish it you can, violates the rules of English syntax. However, it has clear semantics. What Yoda is saying is that you must identify your fears before you can overcome them. Conversely, colorless green ideas sleep furiously is perfectly grammatical English, but it has no meaning whatsoever. It doesn't mean anything for something to be both colorless and green. It doesn't mean anything for an idea to have color. It doesn't mean anything for an idea to sleep. It doesn't mean anything to sleep furiously. It is completely and utterly without meaning. Now, Noam Chomsky used the sentence, colorless green ideas sleep furiously, to make an argument that semantics and syntax are importantly distinct, and that specifically models of models of semantics are insufficient to account for syntax. So what I'm going to be showing you today is that a vector symbolic architecture based model can, first of all, that is designed to learn semantics, can be extended to pick up quite a bit of syntax, demonstrating that semantics and syntax are best understood as on a spectrum rather than as wholly distinct. So distributional semantic models are a type of computational model of human language. They're also known as word embeddings. The way they work is you give a distributional semantics model some large amount of text, such as, let's say, all of English Wikipedia, or even something even bigger. And the model reads the text using, let's say, a moving window that reads it sentence by sentence, some number of words at a time, let's say 5 words at a time, and then it learns the relationships within that window. So there's a number of distributional semantic models that are out there. There's Word2Vec, there's GloVe, the oldest is latent semantic analysis. Some neural models such as BERT can be used. So the one I'm going to be focusing on, though, today is BEAGLE, which is based on holographic reduced representations, which were developed by Tony Plate. BEAGLE was developed by Michael Jones and Doug Newhart in 2007. And basically, distributional semantic models have been enormously influential since the very first one, latent semantic analysis, came out. Like, type latent semantic analysis into Google, and you get nearly 500,000 results. The way distributional semantic models work is they represent the meaning of each word as a vector. So it's a lot like a semantic pointer. It's in Chris Elias-Smith's terminology. And the distance between these vectors shows how similar the words are in meaning. So, for example, we can see that teacher and student are quite close together in meaning. And so they're close together in the space. Similarly, school, college, and university are all just different ways of saying school, really. And so these vectors also become very close together in space after you train the model on language. So my background is in human memory. And human memory can be thought of as a network of concepts, where each concept, which we can think of as vector in a high-dimensional space, are interrelated. So, for example, I have a memory of having breakfast this morning. So for breakfast, I had a bagel sandwich with an egg in it. And the way computational models of human memory work is they're sensitive to 1 degree of separation between concepts. So concepts are interlinked by an experience. So this experience of breakfast, this memory of breakfast, interlinks the concepts of breakfast, this morning, bagel, and egg. And so these concepts will all be interlinked in the web of the network of concepts that makes up human memory. And so while computational models of human memory are sensitive to this interlinking, distributional semantic models that learn language are actually not just sensitive to these direct interlinking between concepts when they occur together, but are also sensitive to concepts at 2 degrees of separation. So for example, distributional semantic models don't just recognize the interlinking between bagel and egg and breakfast, because I had those things for breakfast this morning, but they also recognize the interlinking between bagel and donut. And despite the fact that bagels and donuts are not something you usually eat together, because one's kind of a dessert item and one's a breakfast item, but they are both torus-shaped bakery items. So they are very similar kinds of thing, even though you rarely eat the 2 of them at the same time. So this sensitivity to 2 degrees of separation between things becomes very important for processing language. So what I'm going to be exploring here is what happens when you modify a distributional semantics model to be sensitive to higher degrees of separation. What happens if it's sensitive to 4th order associations, 6 degrees of separation, 8 degrees of separation, and so on. If it's a little bit unclear at this point what I mean by that, I'm going to give you an example. All right, so let's say we have this set of 8 sentences here. Eagles soar over trees, birds fly above forests, airplanes soar through skies, airplanes fly through skies, dishes are over plates, dishes are above plates, squirrels live in trees, squirrels live in forests. Let's consider a corpus that just consists of this 8 sentences. We have trained the model just on these 8 sentences. This set of 8 sentences have a web of interconnections. So what you can see here is that because of the sentence, airplanes fly through skies, we have airplanes and fly have a direct interconnection because they appear together in the same sentence, whereas soar and fly have an interconnection that is mediated by 2 steps. They don't appear in the same sentence, but they appear in similar sentences with the same words. So airplanes fly through skies and airplanes soar through skies. Similarly, trees and forests have this second order association that they're 2 steps away from each other, given this set of sentences. Similarly, over and above. Whereas given this set of sentences, eagles and birds all have a 4-step association. They have to move through 1, 2, 3, 4 words to get to each other. And so you need a model of sensitive to 4th order association to recognize that there's a relationship between eagles and birds here. All right, so in real English, rather than this little toy example, 1st order associations, when words appear together often, indicates topicality. That is to say, words have shared topics. So for example, tiger and stripes, because tigers have stripes, are 2 words that have a strong 1st order association. They often appear together. A paradigmatic or 2nd order association indicates synonymy, such as tiger and lion or tiger and jaguar. Those are words that appear with the same words, even if they don't appear together that often. And that means that they have kind of shared meaning, that they can kind of substitute for each other. It's not, however, clear immediately what does a 3rd order association look like in real language, or what does a 4th order association look like in real language? What do these associations look like? Eagles and birds in real English have strong synonymy. There's actually a 2nd order association example. So we're going to look at what 3rd order and 4th order associations look like in English in a moment. But first of all, we have to build a model that can detect these 3rd order and 4th order associations. So the model we're going to use is BEAGLE. I'm going to go briefly over how BEAGLE works using the toy sentence, eagles soar over trees. So the way BEAGLE works is it has a pair of vectors that represent each word. One vector is an environment vector, and it's randomly generated, and it just represents, in principle, what the word looks like when written or sounds like when spoken aloud. There's also a memory vector, and the memory vector is the one that becomes trained to represent the word's meaning. So given the sentence, eagles soar over trees, we need to update the memory vectors for eagles, soar, over, and trees. So the way to update the memory vector soar is, what we do is we replace soar with essentially like a blank with a special vector we call the placeholder vector. And then we encode all bigrams, all trigrams, and all tetragrams in this sentence using convolution. So we start off by we associate using circular convolution, since we're using holographic reduced representations, but you could use any kind of binding operator here if you wanted. We bind eagles with the placeholder to represent the fact that eagles come before soar, and we bind over with the placeholder to represent that the word over comes after soar. And similarly, we bind eagles placeholder over, and we bind placeholder over trees, and we bind eagles placeholder over trees. In each case, we're using a permutation, which I'm calling P before, which just encodes the word order. Essentially, the way it works is a memory vector is a sum of all questions to which that word is answer. Essentially, it's a fill-in-a-blank game, and any sentence where soar is an appropriate word to fill into the blank, is essentially what the memory vector for soar comes to represent, is where is soar appropriate to fill in a blank. So my modification of BEAGLE, I call the hierarchical holographic model, and it is just a stack of beagles. We just put beagles on top of each other as high as we like. And the way it works is the second beagle uses the first beagle's memory vectors as its environment vectors. So that is to say, rather than using randomly generated vectors, it takes the previous beagle's memory vectors after it's finished being trained, permutes them to prevent getting into the problem that the previous speaker was describing, where you can have binding operations interfering with each other. So you permute the information to protect it, and then use those as the new input to the next beagle, and construct a new set of memory vectors using that set of environment vectors. And then you can just keep doing that, so that the third beagle uses the second beagle's memory vectors as its, instead of using random vectors, and constructs things out of that. So that's the way it becomes hierarchical. And so at each level, it becomes more sensitive to more remote associations. All right, so just to demonstrate that this works, this is running the hierarchical holographic model on the 8 sentences we saw earlier. And we can see here that at level 1, it's not able to detect the 4th order association between eagles and birds at all. At level 2, it is able to detect the 4th order association. They've become a little bit similar. And at level 3, the third level, the third beagle, further reinforces the 4th order association. You can also see that all levels are sensitive to the 2nd order associations between over and above, soar and fly, and trees and forest. This is still just a toy example, so we need to run this on real English at this point. So I run it on a corpus of novels from Project Gutenberg. And what do these orders of association look like? Well, the 2nd order associations look exactly like what I was showing you earlier, with words with shared meaning clustering together, like school, college, and university. At the 2nd beagle, we have 4th order associations coming into play. And I'm going to look at pure 4th order associations. So I've subtracted out the 2nd order associations just to get pure 4th order associations. And pure 4th order associations are kind of weird looking. We have focusing and derived, we have searching and associated, we have perched and emerged. We subtracted out meaning because meaning is at the 2nd order association level. So what we seem to have left at the 4th order association level is actually something that looks a lot like part of speech. Like focusing and derived are both verbs. Searching and associated both can be used as a verb or an adjective. At the 3rd level, we have pure 6th order associations. At this point, it becomes less clear what's going on. We've got beings, which is a noun, and accord, which is a noun and a verb, course, which is a noun, and sent, which is a noun, loan, which is an adjective, and amounts, which is a noun or a verb. It becomes increasingly less clear what kind of information we're detecting, whether it's linguistically useful at this level, just by inspection. And at 8th order association, we have things that seem to be words that seem to be fairly unrelated to each other. We have must and fraction, which are both a noun and a verb, but we also have a cross and druid, which are cross is a preposition or an adverb, and druid is a noun. All right, so this is just to give examples of what these higher order associations look like, but are they actually useful for language tasks? So let's quantify this. To quantify it, I'm going to use combinatory categorical grammar, which is a theory of linguistics that gives us fine-grained representations of part of speech. So basically, there are hundreds of different types of combinatory categorical grammar types. And it's more fine-grained than noun, verb, adjective, adverb. And so we can use this to classify words with a great deal of specificity. So I constructed essentially combinatory categorical grammar vectors, which are very sparse vectors that show how frequently each word is each combinatory categorical grammar type. Then I constructed a word-by-word cosine matrix for both the combinatory categorical grammar vectors and the BEAGLE vectors. And then I compared these two cosine matrices using a Spearman correlation coefficient. So what we find is that as we go up from level 1 to level 2 to level 3 of this tower of beagles, the correlation to the combinatory categorical grammar types gets stronger, which rather suggests that we're the fourth order associations at the second level of BEAGLE, and the sixth order associations at the third BEAGLE are in fact picking up important information about the part of speech of the words and how they're used linguistically. However, the fourth level, which has eighth order associations, is proving to be completely useless, it looks like. All right, so let's look at a grammatical task. The grammatical task is going to be ordering words into grammatical sentences. So I give my model a set of words, which could be, let's say, a corner in robot, there was. And the model has to figure out how to arrange those words into a grammatical sentence. And so let's say there was a robot in the corner is a grammatical arrangement of those words. And I use a very simple model to do this. I use an exemplar model. And so the way this works is my model has 125,000 example sentences to work from. And basically all it does is it tries to figure out which of the example sentences is most similar to this scrambled set of words I've given it, and then use the word ordering of that example sentence to produce a grammatical sentence. And the exemplar model is also either uses the first level vectors, the second level vectors, or the third level vectors, or randomly generated vectors as a control. I also play with another dimension here, and that's whether I am using, how big are the n-grams that I'm using. 5 gram, 11 gram, 21 gram, or I go up to a full sentence when I encode the n-grams. And so essentially what we find is that there is a big improvement from using like standard BEAGLE over random vectors, which means that this task is easier if you know what words mean, not surprising. But there is a significant improvement if you move from second order associations to fourth order associations, which shows that the fourth order associations do contain some important syntactic information. If you go to level 3, it becomes a little bit muddier. And performance decreases for most of the versions of the model at level 3, except for the 21 gram model. So there's an interaction effect going on here between the abstractness of the associations the models are sensitive to and the size of the n-grams it's processing. We can break this down. And here we see that performance essentially peaks for level 1, performance peaks at like 3 grams. For level 2 of the model, performance peaks at 5 grams. And for level 3 of the model, performance is still climbing at 7 grams. So we have an interesting thing kind of going on here, which is that these more abstract associations are more useful if you're using larger n-grams. The reason for this is if you have, let's say, the n-gram, the bigram you are, and the bigram he was. These you are and he was, we can look at Google Books, we can see both of these bigrams are extremely frequent. They happen a lot in English. Google Books doesn't actually look at 7 grams because they are so infrequent, they're not considered useful linguistic information. But strong as an ox is a 5 gram, and it occurs, even though it's such a cliche in English to say strong as an ox, it occurs very infrequently. Whereas, say, this 5 gram gregarious as a locust occurs not at all in English. Now, the thing is, at high levels of abstraction, yours gregarious is a locust and he was as strong as an ox are actually extremely similar sentences. And so by moving up to high levels of abstraction at very high levels of order association, the model becomes sensitive to this similarity. So then we can use the model because of this sensitivity at high levels of abstraction to similarities between sentences. We can use the model to detect that colorless green ideas sleep furiously is a grammatical sentence. So here we're showing that at level 2 of the model, it's able to detect that colorless green ideas sleep furiously is much more grammatical than the ungrammatical alternative, furiously sleep ideas green colorless. All right, so I'm going to wrap up quickly since we're running out of time. But sensitivity to fourth order associations at high levels of this model, the second level of this model, reinforce relationships between words that share part of speech, correlates with theories of syntax, specifically combinatorial grammatical grammar, and improves the ability of the model to order words into grammatical sentences and the ability of the model to judge grammaticality of meaningless sentences. And this provides evidence that part of speech of words exists on a continuum with syntax, and higher levels are more useful when using larger n-grams. So thus we hypothesize that human memory is able to use varying levels of abstraction given expertise. Future work will be looking at seeing whether we can get a model that uses multiple levels at varying degrees of abstraction. They outperform a model that uses one level at a time. And particularly, we might be able to use machine learning to figure out the optimal combination of different levels of abstraction for different n-gram sizes. All right, that's my talk.
All right, thank you, Alex. You're right on time. So we still have time for a few questions. So let's see. We have a question in the chat. Might the introduction of hierarchy improve other word embeddings such as word2vec and glove?
I think the short answer is yes. I think the introduction of hierarchy could improve word embeddings such as word2vec or glove. I tried to figure out how to actually implement this in word2vec, and it's very easy using a vector symbolic architecture to do this kind of hierarchical maneuver. It's less easy to figure out how to do that with word2vec. That being said, I think it's possible that something similar is going on inside of some of the deep learning architectures. So I've done some recent work analyzing BERT, and in terms of its ability to handle like tasks where it processes like syntax and syntactic priming. And I found that the mid layers of BERT, which is a deep neural language model, are best able to process syntax. I think the reason for that is that it's also the most abstract level, because in a neural network, the mid layers are the furthest removed from the output or the input. So it's possible that some of the deep language models that are being very popular in natural language processing right now are already automatically doing some of this abstraction process. And that this is sort of a vector symbolic way of doing that abstraction. I think that's interesting also from an explanatory AI perspective, is that this could be used as a tool to better understand what some of the deep neural language models are doing inside of them.
You mentioned using whole sentence n-grams. I just wanted to ask, do you use a stop list?
I wasn't using a stop list because I was interested in, I guess, syntax, and often articles can carry important, I guess, syntactic information. So, and the other thing is you can compute like whole sentence n-grams like really efficiently using certain vector symbolic architecture techniques. So like you don't have to compute like each n-gram, like it takes the same amount of time pretty much regardless of the n-gram size.
Okay, thanks. I suppose one thing I was thinking about is when we were doing our document comparisons, we used a weighted sort of twist on the n-gram approach to create the document comparisons of the Old English, New English Hamlet. And one of the worries that we had was that it was just matching on all the you know, preposition style words, all the the's and the ands and everything. So I tried filtering those out as well.
Right. I think the original Beagle did use a stop list, which is, I think, reasonable, particularly if you want to just focus mainly on like kind of more purely semantic information. It was only because I wanted to do a sort of a more syntactic application that I left the stop list words in.
Yeah, and also I can see when you're trying to learn word meaning rather than sort of matching on sentences and documents, that it's fine to leave them in, thinking about it.
That being said, one thing I have heard is sometimes do like a principal component analysis. It's sometimes useful to like throw out like the first components. I think another researcher who works with Beagle did a principal component analysis of Beagle vectors and threw out the first component. And that was like the really high frequency words that didn't tell them very much.
I see, yeah.
And then that actually improved their vectors for their particular application.
Okay, thank you.
All right, last question, if any. Well, if not, then please, as I said before, yeah, I'm sorry, anybody?
Yeah, I have a question.
Yeah, go ahead.
So, yeah, when you were embedding one Beagle over another, I actually thought that you were going to capture some very abstract stuff. So, did you find that higher order association that was your hypothesis, or you just put one Beagle over another and you see what happened?
I had an intuition that it might help with part of speech, and that seemed to be borne out by experimentation. I also looked at some other thing. I tried to looking at whether it helped with some semantic stuff, more abstract semantic information. And I found that the first level Beagle actually captured semantic information just fine. Even fairly what we think of as abstract semantic relationships are still captured at that first level. So it only seems to be, as far as I could tell, it was only like syntactic information that really emerged at the higher levels, which I kind of had to experiment to find out that it was more or less only the syntactic information, but at least my intuition that it would at least capture syntactic information seemed to be borne out.
Okay, yeah, thank you.
All right, looks like we are running out of time for this time, but in my opinion, we had two great talks today. It's a lot of information to digest and think about. So once again, if you have any questions to the presenters, please use our VSA mailing list or contact the presenters directly. If you don't know their addresses, you can send email to me. Right, that's it for now. I just want to remind you that we have one unfilled slot on the 27th of July on the last webinar for this session. So we will resume the webinar series in September. So if you want to present on the last occasion, so please contact me. Otherwise, thank you for today, and I see you in 2 weeks for another 2 great talks. So thank you very much. Bye.